Hi everyone. Today I will be presenting about the final project of computer programming. My name is Panupon Warachanon.
My name is ภัสกรวิชัยขัดขาว
So let's begin.
Let's begin with task 1. This slide show the wiring diagram. I used to connect the RGB LED module and the buzzer to the M5 stack. Pin 21, 22, and 19 control the red, green, and blue LEDs. Meanwhile, pin 17 it output the temperature indicator. This wiring is important because this exact pin number appear in my code later. So everything I do in software depends on this hardware setup. In task 1, the goal was to create an alarm that can be turned on and off from Blink and also stop locally using button A. So the first part of my code define a variable called alarm on. This variable is the heart of the alarm system. Whenever the alarm is supposed to active, this variable become true, and every part of my code check this variable to decide what system should do. By having one variable control the entire alarm, I can keep both the physical bottle and Blink app synchronized. Next, to make the alarm beep, I didn't use delay because delay would feed the program instead. I used a non-blocking timer using the millis function. The code checks if 1 second had passed. If the alarm is on, the buzzer play a short beep using the command m5.speaker.tone 1000 and 120. This make a 1000 Hz beep for 120 milliseconds. Using Muse keeps the entire device responsive while still making the alarm beep every second. This part of the code handles the two-way. The alarm can be controlled. If the user press button A code immediately, set alarm on to false, stop buzzer, and update the blink switch to off. This ensures the app always shows the correct state. On the other hand, when the user toggle the switch in Blink, the function blink write v0 runs. It reads the value from the app and set alarm on accordingly. This makes alarm fully controllable from both the device and the app with no mismatch. Result 1 Remote alarm system resolve. And here we have the final output of task 1. The alarm beeps every second when it is active. Button A stop in it instantly. The Blink app and the device always show the same status. And the serial monitor prints every action which helps confirm that the code works exactly the way it should. And now moving on to task 2. In this task, I create a system that let the user turn on red, green, or blue from Blink app, but only one color at a time. So I created a variable called LED color. This variable store which color is currently selected, 1 for red, 2 for green, and 3 for blue, and 0 when everything is off. This function is what enforces the exclusive LED behavior. The code first turns off all LEDs by writing low and to all 3 pins. Then, depending on the value passed to the function, it turns only on LED. So, for example, if the user select red, the code called set exclusive color 1, and only the red LED turns on, while green and blue remain off. One challenge in IoT is making sure the app always show the correct state. So after changing the LED color, I update Blink switch using Blink Virtual Light V1 LED color 1, Blink Virtual Light V2 LED color 2, and Blink Virtual Light V3 LED color 3. This means if red is active, only the red switch in the app show on. This prevents two color buttons from showing on at the same time. And task 2 result. And this is a result. The RGB LED response is instantly to the Blink app. Only one color can ever be on at a time. The app always updates itself correctly after every change. This gives us a clean and reliable LED system.
And now for task 3, I use a DHT sensor to measure temperature and humidities. Instead of sending data to Blink constantly, I only send update when the value actually change. And to be able to do that, I store the last value sent to Blink. And the code read the sensor using Anatomilis timers. So every 5 seconds it runs using the function called the DHT read humidity and temperatures. And this gives me a fresh reading without overloading the processors. Then the code check whether the new temperature or humidity is different enough from the old values. For temperature, it's must change more than 0.5 degrees. And for humidities, it must change more than 1%. If the value haven't changed enough, the code prints no brick change, not sending. So this prevents unnecessary cloud communications. And when the value do change enough, the code convert the temperature into Celsius or Fahrenheit, depending on the user preference. Then it send the value to Blink using the function Blink Virtual Write V5 and V6. The M5 stack screen also update using M5 LCD prints, which give the user instant feedback on the device. And to the result, the temperature and humidity is updated every 5 seconds, and the app only receives new data when the change occur. User can switch between Celsius and Fahrenheit, and both the app and the screen show accurate readings. So onto the task 4. The task 4 add a smart features called comfort mode. When comfort mode is on, the LED automatically change color based on temperatures. And to do that, I create a function that return a color code depending on the temperature range. The temperature to color functions work like this. If the temperature is below 24 degrees, the function return 3, which correspond to blue. Between 24 and 28 degrees, it's return 2, which is green. And when above 28 degrees, it's return 1 for the red. This make the LED behave like a temperature indicators. And in this part of the code, I check whether comfort mode is active. If it is, the system ignore all manual LED buttons. Then it's look at the current temperatures and determine the correct LED colors and call the executive color functions to update the LED. And finally, the blink switch update automatically so the app always shows the correct colors.
In conclusion, throughout this project, I combine hardware, IoT, and communication and sensor logic into one complete system. Task 1 taught me synchronization between physical button and blink. Task 2 taught me clean and exclusive RGB LED control. Task 3. Focus on efficient sensor reading and cloud communication. And Task 4. Introduce intelligent automation based on temperature. All the code works together to create a responsive, efficient, and smart IoT device. Thank you.